So for day 2, for 8-1 day 2, we're going to focus on series. And here's what a series is, okay? If I take the numbers in a sequence and I add them all up, the sum of the numbers in a given sequence, that's a series. So essentially, that's why sequences and series are related. The sequence is just a bunch of numbers. The series is the sum of those numbers, okay? And there's some new notation that we're going to see, and then some different strategies that we're going to use. However, how we found the terms in our sequences is going to be similar. We'll have some type of mathematical definition that we use to find the numbers in our series that we add together. As I mentioned in sequences, there are two different types of series. The first one is an infinite, so if we look at an infinite series, that's for an infinite sequence. So the terms that go on and on forever, the sum of those is represented this way. We're going to spend most of our time working with what are called finite series, okay? And so that's called the nth partial sum. So if I'm only finding the first 5 terms, that's the 5th partial sum, that kind of thing. So essentially, when it does end, and we add them up, we have a finite series. We use this capital sigma. This is a Greek letter, and we use that to represent our series or summations, the summary when we add them up. And so we have to talk about that notation a little bit. All right, so here's the summation notation that we use to represent a finite series. So here's the series, S sub n. Now, what we have here, here's where the sigma notation comes in. So in this particular case, the index they use is I, meaning we're going to start with 1. So we're going to find the first term, and we're going to add all the way up to the nth term, whatever that may be. So this would be the first term, then we go up to the second, third, fourth, whatever n ends up being, and that's where we end. And then we're going to just add those terms up. Okay, so this is the summation notation that we use for series, and we want, the lower this number is, the less number of terms we're going to have. So a lot of the time, if it was n and it just went on forever, we'll have a different notation up here, and there you'll see an infinity symbol. But when it's n, what it's inferring is that it's going to end somewhere with some number. And we'll go through some examples here that'll hopefully clear that up for you. Okay. And here's the infinite series, as I mentioned. So the difference being is it'll end at infinity and it'll just go on and on forever. So here it has an ending, the nth term. When this top limit, this upper limit is infinity, it doesn't have an ending. And you say, well, how do you add something up that never ends? Well, we'll look at some problems like that later, and you'll see why that makes a little more sense. All right, let's just get into some examples of problems that you're going to have to do. And essentially what you're going to do is you're going to evaluate these series, evaluate the sum of each of these series. So again, we're given this definition for A, another definition for B, and notice that in this case, they use I for the index, but in this case, they use K for the index. And they'll use different variables from time to time. Don't get this confused, and for any of you who maybe saw this somewhere, there was Burger King in our little pandemic, in our quarantine. Burger King has been putting out these math formulas where you can win free food. And in one of the problems, it looked a lot like this. Hopefully you didn't look at this I and think of the imaginary number, because that's not what it is. I is the index. So anyway, as an aside, in case you saw that and we're trying to figure out how to do that one. So here's what we're going to do. We're going to find the first, second, third, fourth, fifth terms and add them up. That's all that this really means. Here I'm going to find the third, fourth, fifth, and sixth terms, add them up. Okay? So let's just go ahead and start with A. So what I'm going to do is I'm going to start with the first term. So I plug 1 in for I, and so this is 2 times 1 plus 3. So this is just like what we did on day 1 now, right? I'm finding the first term. So this is 5. Okay, now I've got to find the second term. So I plug 2 in. 2 times 2, that's 7, etc. all the way up to the fifth term. So go ahead, pause the video, find the next 3 terms, add them together, and see if we get the same thing. All right, so the third term is going to be 2 times 3 plus 3 is going to give me 9. I mean, hopefully you start to see that there's a pattern here. So the next term is going to be 11. The next term is going to be 13. And I just have to add those up. That's what you get. So the series is, again, how this differs from a sequence. You're putting plus signs in between them instead of commas. Okay? So that's how you find a series. All right. If you want, pause the video, go ahead and give B a try and see what you end up with. Obviously, there's a little more going on here with B because I have K as both a power and a denominator. So you're going to have to plug that value 3, 4, 5, and 6 in both places. Okay, so go ahead and give that a shot, and then we'll come back and go through it. All right. So again, I need to. Here's my definition. I need to find K when K equals 3. Now I start with 3. Okay. So notice I plugged 3 in for K in both places. So negative 1 to the third is negative 1, which makes this negative 1/3. Then I plug in 4. K equals 4. So negative 1 to the fourth, that's positive 1. So positive 1 times 1/4 is 1/4. So this is plus 1/4. And now I just keep going. Now I plug 5 in. Negative 1 to the fifth is negative 1. So this is negative 1/5. And then lastly, negative 1 to the sixth, which is 1 times 1/6 is plus 1/6. And then you need to get a common denominator and change your numerators where necessary, or I'm certainly guessing that many of you just reached for your calculator and did it that way. Either one. Bottom line is I get negative 7/60. Whenever you do problems with fractions, you must always reduce, and that we should already know. I have one more example that I want to go through because you. So here is an interesting problem, because if you notice here, we've got the lower index is 1, we go from 1 to 6, but there's no n in here. And so what this means is that whenever we would quote-unquote plug in a value for the index, there's nowhere to plug it in, which means it's always equal to 3. So essentially what this means is the first 6 terms, or the first however many terms, will always just be 3. And so it's 1, 2, 3, 4, 5, 6. There's nowhere to plug that in, but there's still 6 terms. So of course that's 18. And that's how you would do something when it's a constant. The numbers in that series are just always the same. They don't change. There's nowhere to plug it in.